When you're looking at the top half of your guys' handout, you can see it says atoms bonding and, actually it says boating. Apparently there's a typo there. So atoms bonding and periodic table is what that should say. And what we're going to talk about is all of this stuff, valence electrons, protons, and electrons. And we're going to decipher how does this actually play a role in those chemical changes that we saw yesterday. So the matchstick, the little tablet we put in the water, what exactly is going on in those scenarios at the atomic level? That's what we're going to try and figure out. So let's start with a valence electron. What is a valence electron if you were to define it? When we're defining a valence electron, we're going to call it the electrons in the outermost shell. And here's the take-home message for today that we're adding to that. You guys knew that it was those electrons in the outermost shell. You knew it was those outer ring. Remember the example of the stadium? How if we were to fill up a stadium, that ring of bleachers that was closest to the field is the seats that you fill up first. And then when those seats become full, you go to that next outer ring. So it's that outermost ring. You fill up the innermost part first, then you work your way out, filling up the rings. In the innermost shell, how many electrons can we hold? Carter? It's 2. So we can have 2 electrons in the innermost shell. The next shell, if we had 2 energy levels, how many could fit? 8. So we have 2, 8, and then my last one, the one that we worry about in this class, the third energy level can hold how many, Bailey? 8. So 2, 8, 8. If there's 2 on the inner ring, then the next electron that comes in has to fill the next outer ring. Correct? Here's the part that we're going to add for today. These electrons in the outer shell are going to help determine whether a chemical bond occurs or what the chemical properties are. So valence electrons help determine the chemical properties for that element. So we're going to spend a little time today to figure that out. And even Mrs. Larson has an activity then that you guys will be moving into after we get through today's activity tomorrow that will also tie back to that. What do we mean by all these chemical properties? We know what a chemical change is, right? Who can define that for me? A chemical change. We talked about it yesterday over and over again. Landon?
It's where you mix like 2 substances and then it turns into 1 substance.
Okay, so not necessarily just 2 substances turning into 1, but it's a change in the substance itself.
Yeah.
It's no longer that original substance. The wood of the matchstick, was it wood after we lit it on fire?
Nope.
It was ash, right? That's not wood. But what is it? Why is it that that happens? Okay. Now we have these little diagrams that are called electron dot diagrams, also known as Lewis dot structures, and we're going to talk about those and do a little activity with those today. An electron dot diagram is just going to be indicating the valence electrons. We ignore all the other electrons. Okay, so it's including the symbol. So what's the symbol for hydrogen? H. So my symbol for hydrogen would be H, for example. So it includes the symbol and the valence electrons surrounding it. So how many valence electrons does hydrogen have? So when we look at hydrogen, we know it has 1 valence electron. And so an example of an electron dot diagram would be hydrogen, the symbol with just a dot next to it. And it needs to be to the right. We'll talk about that in a little bit, why it goes to the right. Now, can somebody explain to me, how do we know the number of valence electrons that an element has? How can you find that really easy using that periodic table of yours? Dane?
The top numbers, and then just take off the 1, because there's 10 right here. Well, that's
So what do we call those columns on a periodic table? Landon?
We call them groups or families.
Good. So those groups, the group number indicates the number of valence electrons. Skipping over the 10 transition metals, great. I'm glad you added that, Dane. We skip over those when we're counting across, and essentially the group number it's in tells us the number of valence electrons it has. So if I asked you how many valence electrons does, let's do beryllium have, what would you come up with? So beryllium is BE. Jaden?
Oh, 2.
2. Good. So then we would have 2 valence electrons. And we're going to talk about exactly where to place those. The last word that I want to define for you is chemical bonds, which is the force of attraction that holds the atom together. So a chemical bond is some sort of attraction that keeps these atoms together. And that's because of, so you might want to add that in. You could say because of, you could write it however you want, but that's because of the arrangement of the electrons. So due to arrangement of electrons. So now that you guys have kind of an idea of what we're moving into, now I'm going to talk to you about what that means as a result of the metals, metalloids, and nonmetals. Raise your hand if you've ever heard of metal, or a nonmetal, or a metalloid. Remember, we went through those properties. Something you're probably going to want to go back and review, but there's something else you need to know about those 3 things. Okay? We're talking about the electrons on a metal, the electrons on a nonmetal, and the electrons on a metalloid in this case. Metals react by losing valence electrons. So they're the givers. Okay? How many of you like to give presents? You like to help people out, right? These are our givers. So our metals react by losing electrons. The nonmetals are going to become stable as a result of gaining electrons. So think of it this way. If the metals are giving away electrons, who's taking them in? The nonmetals. Good. So we have become stable. By gaining, or, so they either gain them all the way or they share electrons. There's one exception to these nonmetals. So if you're looking at your coloring the periodic table, I would like you to look at hydrogen. Is hydrogen a metal, nonmetal, or metalloid? Hydrogen itself is a nonmetal, and it breaks this rule. Hydrogen is going to be more like a metal in the sense that it's going to give away or share its electrons. So you want to put like a little star here, something that you're going to go back to and write except hydrogen. So looking at your coloring the periodic table activity that we did, you guys know that hydrogen is a nonmetal. However, it's going to act more like a metal in this case. All the other ones that you guys know about, all the other metals and nonmetals you know about, are going to follow the rule listed above. Our last one, the metalloids, they're my in-between people. They're the, we can take them or we can give them. So they're the ones that I think are a little bit more complex. We don't really know for sure just by looking at the periodic table right now with what you guys know what they're going to do. But eventually you're going to learn some tricks to be able to look at them and figure out what they would do. So metalloids can gain or lose. Now, when you look at this back side of your notes page, what you're going to see is it says Lewis dot structures show blank. So what we're going to talk about first is that they show your valence electrons. It's just like the electron dot diagrams that we talked about just on the other slide, but you need to be pointing out that these Lewis dot structures show valence electrons. Buttons. And the valence electrons are the place where chemical bonds occur. So valence electrons are the place where chemical bonds occur. Whoops, I made a typo in there. So for the pattern in which these dots fall, I want you to look at that little box. And I want you to pay attention to these little numbers that are all around the box. And when we add dots to a symbol, depending on how many they have, we add them in this pattern. We add it to the right side, the top, the left, and the bottom. And then when we're still adding dots beyond 4, then we add them to the right, top, left, and bottom again. So for example, if you're looking at barium, okay, find it on your periodic table. And if you look at barium on the periodic table, what column is it in? Landon?
2.
It's in column 2. So barium, being in column 2, has how many valence electrons? Jeffrey? 2. And when we draw them on, we draw it in the first position, the second position. Are all the valence electrons drawn?
Yeah.
We have the symbol, right? We have Ba, so we have the symbol, and we have the valence electrons. That's a Lewis dot structure. Pretty simple, right?
Yep.
Makes sense, absolutely. So don't overcomplicate it. Because when we get into this activity, you might try and overcomplicate it, but if you follow these 3 steps, you write the symbol, you write the valence electrons following the pattern, right, top, left, bottom, right, top, left, bottom, you'll be okay. Let's look for indium. Indium is IN on your table. What column is it in, Jessica?
13.
It's in column 13. So we know it's after the transition metals, right? So we know that it has how many valence electrons? 3. Good. So then we draw it right, top, left. 1, 2, 3. Follow the same pattern. 1, 2, 3. And then the last example that I have for you is selenium. Find selenium on your table. Raise your hand when you've found it. Braden, how many valence electrons does selenium have, and how do you know?
6 because it's in column 16.
Great. It's got 6 valence electrons because it's in column 16 or 6B, right? Remember how we have AB numbers? So then we go right, top, left, bottom. That's only 4. So we still need to get 5 and 6 in there, right? So we go back to the right, top, and we're done. Pretty simple. So what you're going to see here on your table is a list of elements. It does not necessarily follow the pattern of your periodic table. So please know that these elements right here are not in column 1, 2, 3, 4, 5, 6, 7, 8 necessarily. But yet they might be. So we're going to look at that. Then what you're going to be doing is you're going to get out a piece of paper. You're going to start with hydrogen. You're going to put an H on your piece of paper, and you're going to have an object to represent your electrons that you will set down. If you are placing that object in the correct position, meaning position number 1, and you're representing the correct number of valence electrons, then you will have a container to keep it in, and you'll move on to the next one. Now, we're going to do the first one, hydrogen, together. So we're going to get set up for this. I need you all to get out a piece of paper starting